DeepSeek v3 is a state-of-the-art mixture of experts MoE language model with 671 billion total parameters, of which 37 billion are activated per token. It incorporates multi-head latent attention MLA and DeepSeek MoE for efficient training and inference, continuing the architecture innovations of its predecessor, DeepSeek v2. The model pioneers two strategies: an auxiliary loss-free load balancing mechanism to maintain computational efficiency without degrading model performance, and a multi-token prediction MTP objective for improved training signals. Pre-trained on 14.8 trillion diverse tokens, DeepSeek v3 demonstrates excellent performance across benchmarks while maintaining cost efficiency and stability during training. Architecture: DeepSeek v3 builds on the Transformer framework, featuring multi-head latent attention MLA for compressed key-value caching and efficient inference. It employs DeepSeek MoE for feed-forward networks FFNS, allowing finer-grained expert selection. The model introduces auxiliary loss-free load balancing to prevent routing collapse and reduce computational inefficiency during training. Additionally, the multi-token prediction MTP objective enriches the training process by enabling predictions for multiple future tokens, enhancing data efficiency and overall model performance. Low-rank compression for key-value KV storage. Step 1. Compute compressed KV representations. Instead of storing full-dimensional key and value vectors, MLA compresses them into a latent vector, using a down projection matrix. Step 2. Compute key representations. From the compressed vector, the model reconstructs the compressed keys, using an up projection matrix. Additionally, a decoupled positional key is computed using rotary positional embedding ROPE. Finally, the total key vector used in attention computation is the concatenation of the compressed key and the positional key. Step 3. Compute value representations. Values are processed in a similar way using an up projection matrix. Compute final attention output. The final attention scores are computed using the softmax operation on the scaled dot product between queries and keys. DeepSeek MoE. 1. Compute the final FFN output. The output of the FFN for token T is computed as 2. Compute the gating value. Each token selects a few routed experts based on affinity scores. 3. Compute the token to expert affinity. The affinity score is calculated as multi-token prediction MTP. 1. Compute the token representation at each prediction depth. For the KTH MTP module, the token representation is computed as. This combination is passed into a transformer block for further processing. 2. Compute the final representation for token prediction. The new token representation at depth K is the transformer block. TRM refines token representations for better prediction. 3. Compute the probability distribution of the next token. Outhead maps the representation to logits. Softmax is applied to get probabilities for predicting the next token. 4. Compute cross-entropy loss for training. The model compares predicted probabilities with actual ground truth tokens. Loss is computed separately for each depth. The overall MTP loss is an average of all depths, weighted by infrastructures. DeepSeek v3 utilizes a cluster of 2048 NVIDIA H800 GPUs interconnected via NVLink and InfiniBand. The training framework integrates pipeline, expert, and data parallelism, supported by efficient algorithms like DualPipe. DualPipe reduces pipeline bubbles and overlaps computation and communication phases, minimizing training delays caused by heavy communication. Memory-saving techniques, such as recomputing intermediate activations and asynchronous updates, ensure that training remains scalable and cost-effective. DualPipe. DualPipe is a novel pipeline parallelism algorithm designed for efficiency in large-scale MoE training. It overlaps forward and backward computations with communication phases, effectively addressing cross-node communication overhead. Using bidirectional scheduling, DualPipe reduces pipeline bubbles and sustains high throughput, even with large model scales. This approach also optimizes GPU utilization by dynamically allocating computational and communication resources. FP8 Training. To enhance efficiency, DeepSeek v3 incorporates FP8 mixed precision training, enabling faster computation and reduced memory use. Key operations, such as GM, run in FP8, while critical components like normalization and gating maintain higher precision. Advanced quantization techniques mitigate the effects of outliers in activations and weights, ensuring stable training dynamics. FP8 training significantly lowers computational costs without compromising accuracy, validated on large-scale models similar to DeepSeek v2. Mixed Precision Framework. DeepSeek v3's Mixed Precision Framework balances computational speed and numerical stability. Most operations are conducted in FP8 for efficiency, with sensitive components preserved in BF16 or FP32. The framework employs fine-grained quantization and higher precision accumulation to mitigate errors associated with low-precision formats. This hybrid approach allows DeepSeek v3 to leverage low precision for scalability while maintaining robust performance. How DeepSeek R1 reinforcement learning work? Group Relative Policy Optimization, GRPO. GRPO replaces the traditional critic model, a large and computationally intensive component in typical reinforcement learning setups, to save training costs during reinforcement learning. Here's how GRPO works. Group sampling. For a given query, a group of responses is sampled from an older version of the model's policy. These responses are scored based on predefined rewards like correctness and clarity. Baseline estimation. Instead of using a separate critic model, GRPO calculates the baseline for optimization directly from the group scores. This avoids the need for an additional, large model during training. Optimization. The policy is optimized by comparing the probabilities of sampled outputs under the new and old policies. A clipping mechanism ensures stable training by preventing extreme updates. Cost efficiency. By eliminating the need for a separate critic model and leveraging group scores for optimization, GRPO significantly reduces computational requirements while maintaining performance. Thanks for tuning in, and we'll see you in the next video.